There is something inside you right now that has existed for longer than the Earth. Not your memories, not your name, not the body you know, but the atoms inside you, the iron drifting through your blood, the carbon threaded into every cell. Those atoms were forged inside stars that burned and collapsed billions of years before this planet even formed. You are, without exaggeration, made of the oldest material in the universe. And somewhere out there, roughly 10.5 billion light-years away, sits an object that may have helped create the conditions that made stars like yours possible. It has no name you could speak aloud in a way that does it justice. Its catalog designation is TON 618, but that label, 3 letters and 3 numbers, hides something so extreme, so structurally impossible seeming, so far beyond anything the human brain evolved to imagine, that spending a few quiet hours thinking about it carefully might genuinely change the way you understand your own existence. So tonight, wherever you are, whatever brought you here, whether you are lying in the dark trying to let your mind slow down, or sitting somewhere quiet needing something bigger than your problems to fill your thoughts, I want to take you there, not with urgency, not with alarm, with the kind of slow, careful attention that something this extraordinary deserves. We are going to move through it together, layer by layer, letting each idea settle before we reach for the next. And by the end of this journey, you will not just know facts about a distant black hole. You will feel, in whatever way a human being can feel something 10 billion light years away, the actual weight of what it means for something like this to exist in the same universe as something like you. Before we go anywhere, I want you to take a breath, a real one. Let your shoulders drop. If you are in bed, feel the surface beneath you, the specific texture of where you are in this moment, because that is where we are starting, right here with you, before we travel anywhere. And I want to acknowledge that traveling in thought is the only kind of travel that covers these distances. No spacecraft we have ever built, no spacecraft we could ever reasonably imagine, could cross 10 billion light years within any time frame that matters to a human life. What we are doing tonight is something that only minds can do. We are reaching across time using nothing but physics and curiosity, and that, honestly, is its own kind of miracle. Now, let us start not with the black hole, but with light. Right now, light is traveling toward you from the sun. It left the surface of the sun about 8 minutes ago, crossed roughly 150 million kilometers of space, passed through the upper atmosphere of this planet, and if it is daytime where you are, some of it is probably touching your skin or illuminating the room you are in. 8 minutes. That is how long it takes sunlight to reach you. That number feels manageable. It fits inside your sense of time. Now stretch that slightly. The light from the nearest star beyond our sun, Proxima Centauri, takes about 4 years and 3 months to reach Earth. So when you look at that star on a clear night, you are not seeing where it is now. You are seeing where it was 4 years ago. The star has moved since then. You are looking into the past. Go further. The Andromeda Galaxy, the nearest large galaxy to our own, is about 2.5 million light-years away. The light leaving Andromeda tonight will not arrive at Earth for 2.5 million years, and the light we see from Andromeda right now left that galaxy 2.5 million years ago, before the genus Homo existed on this planet. When you look at Andromeda with a telescope, you are watching a galaxy as it appeared when our ancestors were barely walking upright. Now, TON 618, 10.4 billion light-years away. The light currently reaching our telescopes from TON 6618 left that region of the universe 10.4 billion years ago. The universe itself is only about 13.8 billion years old. So we are seeing TON 618 as it existed when the universe was roughly 3 billion years old. Less than a quarter of its current age. When that light began its journey, not only did Earth not exist, not only did our sun not exist, the cloud of gas that would eventually collapse to form our solar system had not even begun to gather itself together. The atoms that make up your body were spread across a galaxy that had not yet taken its current shape. And light from this one extraordinary object was already traveling, already crossing the gulf, already on its way toward a planet, and a species and a moment that was still billions of years in the future. Let that breathe for a moment. You do not need to fully grasp it. No one fully grasps it. The human brain is a remarkable organ, but it evolved for savanna-scale problems, for tracking animals, for reading faces, for understanding seasons. It did not evolve to intuitively hold 10 billion years as a living number. What you can do, and what I want to invite you to do tonight, is approach that number with something closer to awe than to comprehension. Not panic, not vertigo, just the slow opening that happens when you realize that ordinary reality is a paper-thin slice of something much, much larger. So what is TON 618 exactly? It is a quasar. That word deserves an explanation because it is one of the most important and most misunderstood words in modern astronomy. A quasar is not a star, though it was originally mistaken for one. When radio astronomers in the 1950s and 1960s first began mapping unusual bright points in the sky that emitted strong radio signals, they assumed they were some exotic variety of stellar object, hence the name quasi-stellar radio source, quasar. But as instruments improved and scientists measured the spectra of these objects, something deeply strange emerged. The light from these sources was redshifted far beyond what any star could produce. Redshift in cosmological terms is a stretching of light caused by the expansion of space itself. The more an object's light is redshifted, the farther away it is, and the faster the universe was expanding when that light was emitted. The redshifts of these quasars placed them at distances so enormous that they could not possibly be individual stars. To shine that brightly from that far away, they had to be releasing energy on a scale that dwarfed anything previously known. We now understand that quasars are the violently energetic cores of very young, very active galaxies. At the center of each one is a supermassive black hole, gorging on infalling gas and dust and stars, converting a portion of that matter into raw energy with an efficiency that makes nuclear fusion look wasteful. The accretion disk surrounding the black hole, the swirling disk of superheated plasma spiraling inward like water going down a drain, radiates with such ferocity that it outshines every star in its host galaxy combined, sometimes by a factor of thousands. TON 618 is one of the most extreme quasars ever identified. Its luminosity is estimated at around 140 trillion times the energy output of the Sun, not 140 trillion suns arranged neatly across a galaxy. One point, one gravitational engine, one cosmic drain where matter falls in and light pours out with a power that staggers every unit of measurement we have invented. And the black hole driving it, its mass is approximately 66 billion times the mass of the Sun. 66 billion solar masses. I want to stay with that number for a moment, not to rush past it, because the temptation is always to nod and move on when a number becomes too large. But this one deserves the attempt. Our Sun contains about 99.8% of all the mass in our solar system. Everything, every planet, every moon, every asteroid, every comet, every speck of dust orbiting our star, all of it combined amounts to less than 1/4% of the Sun's mass. The Sun itself weighs roughly 2 times 10 to the power of 30 kilograms. That is a 2 followed by 30 zeros. It is already a number that language cannot adequately hold. Now multiply that by 66 billion. The black hole at the heart of TON 608 contains 66 billion times the mass of the Sun, compressed into a region of space defined by a boundary called the event horizon. That event horizon, the invisible spherical surface beyond which nothing can return, has a diameter of roughly 400 billion kilometers. If you place TON 618 at the center of our solar system, its event horizon would swallow Mercury. It would swallow Venus. It would swallow Earth. It would swallow Mars. It would continue through the asteroid belt, engulf Jupiter, pass Saturn, and its outer boundary would sit somewhere beyond the orbit of Neptune, the outermost planet in our solar system. The entire architecture of planetary life as we know it, every world we have ever looked at through a telescope or sent a probe toward, would fit inside the event horizon of this one black hole with room to spare. And that boundary, that event horizon, is not a surface in the physical sense. It has no material to touch, no wall to feel, no transition you could see or sense as you crossed it. It is a mathematical feature of space-time, a threshold defined by geometry, the point at which the escape velocity from the gravitational field exceeds the speed of light. Inside it, every possible path through space-time curves inward. Not some paths, not most paths, every path, even light, which always travels in what it perceives as a straight line, finds that straight lines inside the event horizon lead only one direction, toward the center. There is no outward anymore. Direction itself ceases to function in its ordinary sense. This is not science fiction. This is the direct implication of equations that have been tested and confirmed in dozens of experiments and observations. The mathematics of general relativity, the framework Einstein completed in 1915, predicts the behavior of massive objects with precision that has never failed a test. And those equations describe the interior of a black hole in terms that are perfectly self-consistent, even if they produce results that no human mind can picture from the inside. Now I want to talk about something that often gets glossed over in discussions of black holes, because it changes the emotional relationship you can have with an object like this. The event horizon of TON 618, because of how large it is not a place of extreme tidal forces. This surprises most people. We imagine black holes as places where gravity tears everything apart, where the difference in gravitational pull between your head and your feet would stretch you like taffy, a process physicists actually call spaghettification, which is one of the more honest terms in all of science. And near a stellar mass black hole, one formed from the collapse of a single star and perhaps a few times heavier than the Sun, that is exactly what would happen. The horizon of such a black hole is small enough that the tidal differential, the difference in gravity between nearby points, is lethal. But TON 618's horizon is not small. It is 400 billion kilometers across, and here is the strange geometry of it. Tidal forces depend not on the total strength of gravity, but on how much that strength changes over a given distance. When the event horizon is enormous, the gravity at the horizon is immense in absolute terms, but it changes relatively slowly from one side of your body to the other. Counterintuitively, if you could somehow cross the event horizon of TON 618, you would not immediately feel the crushing doom that the name implies. You might not feel anything unusual at all at the moment of crossing. The horror of it is subtler, and in some ways more philosophical. You would be inside. Every direction you looked, every path you could take would lead you inward, and you would never know from the inside exactly when you had crossed. The universe outside would still be visible, its light still reaching you, but you would be in a region from which you could never send a signal out. No one outside could ever know what you were seeing. No message could escape. You would be permanently, irrevocably, and invisibly cut off from the rest of the cosmos. That asymmetry of information rather than force is one of the most philosophically haunting aspects of black hole physics, and it sits at the center of one of the greatest unresolved problems in modern physics, the information paradox, which we will come back to. But first, let us talk about where TON 618 came from, because the existence of an object this massive, this early in the history of the universe, is itself a scientific problem that keeps researchers awake at night. Standard models of black hole formation begin with stellar death. When a massive star, something at least 20 or 30 times heavier than the Sun, exhausts its nuclear fuel, it can no longer support itself against its own gravity. The core collapses catastrophically in a fraction of a second, and depending on the specifics, the result is either a neutron star or a black hole. A black hole formed this way might start with a mass of 5, 10, maybe 40 times the mass of the Sun. From there, it can grow by consuming gas and dust and other stars. It can merge with other black holes. It can accumulate mass over vast stretches of time. The problem with TON 618 is time. The universe was only about 3 billion years old when the light we currently see from TON 618 was emitted. 3 billion years. That sounds enormous on a human scale, but it is a relatively short window in cosmic history. For a black hole to grow from a stellar remnant of a few tens of solar masses to 66 billion solar masses in roughly 3 billion years, it would need to accrete at near maximum efficiency, essentially continuously for that entire period, and the physics of accretion imposes limits. As a black hole consumes matter, the infalling gas heats up and radiates, and that radiates pushes back against new infalling material. This creates what astrophysicists call the Eddington limit, the theoretical maximum rate at which a black hole of a given mass can accrete without blowing away its own food supply. At the Eddington limit, Even continuous accretion for 3 billion years does not easily produce 66 billion solar masses from a small starting seed. The numbers are tight. They require assumptions that may not hold. And this is why the existence of ultramassive black holes in the early universe, objects like TON 618 and others found in recent years, has forced cosmologists to seriously reconsider the pathways through which black holes form and grow. One leading hypothesis involves what are called direct collapse black holes. In the early universe, before the first heavy elements existed, before the chemical pathways that lead to star formation in the modern sense were available, enormous clouds of primordial gas consisting almost entirely of hydrogen and helium may have been able to collapse directly into massive black holes without ever passing through a stellar phase. These sea black holes could potentially begin their lives with masses of hundreds of thousands or even millions of solar masses. Starting that large, the journey to billions of solar masses becomes more plausible, though still demanding. Another hypothesis involves rapid early mergers. In the first few billion years of cosmic history, galaxies were smaller and denser and closer together. Collisions and mergers were far more common than they are today. When galaxies merge, their central black holes eventually spiral toward each other and merge as well, combining their masses. A series of such mergers in the right sequence could accelerate growth dramatically, and some theorists propose that in the densest regions of the early universe, accretion could temporarily exceed the Eddington limit through mechanisms not fully understood, with infalling gas somehow bypassing or overpowering the radiation pressure that ordinarily sets the ceiling. None of these explanations is definitively confirmed. All of them are active areas of research, and the James Webb Space Telescope, which has been peering into the early universe with unprecedented sensitivity since 2022, is already finding massive black holes in places and at times that push even these revised models. The universe appears to have found ways to build extreme structures faster than we thought possible. TON 618 is not an anomaly to be explained away. It is a member of a growing class of objects that are forcing a fundamental reassessment of how matter organizes itself in the universe. This is one of the things that makes studying objects like TON 618 feel genuinely exciting rather than merely encyclopedic. It is not a closed book. It is an open question written in light that left its source before our planet existed, arriving now at instruments built by creatures who are only beginning to understand what they are reading. Let us talk about what the environment around TON 618 would actually look like in as much detail as physics allows. The center of the system, the black hole itself, is invisible. Not dark in the way a shadow is dark, not dim in the way a faint object is dim, but optically sealed. No photon that passes through the event horizon can carry information outward to anything outside. The interior simply does not exist in the sense of being observable. What you would see, if you could somehow be positioned nearby in a way that physics would not permit, is the accretion disk. The accretion disk of TON 618 is a structure of almost impossible scale. Imagine a flat, fiercely luminous ring of gas and plasma orbiting the black hole at distances ranging from just outside the event horizon out to many millions of kilometers. Depending on how we define the outer edge, the material in this disk is not falling straight in. It is spiraling inward along roughly circular paths that slowly decay. Conservation of angular momentum, the same physical principle that makes a figure skater spin faster when she pulls her arms inward, governs the motion. As material loses energy to friction and magnetic interactions within the disk, its orbit shrinks and it moves inward, eventually crossing the innermost stable circular orbit and falling the rest of the way in. The gas in the innermost regions of this disk is moving at velocities approaching a significant fraction of the speed of light. At these speeds, and under the compressional heating of millions or billions of tons of gas all spiraling together, the temperature reaches tens of millions to hundreds of millions of degrees. At those temperatures, matter does not exist in any form familiar to daily experience. Atoms are completely stripped of their electrons. Protons, electrons, and heavier nuclei exist as a plasma, a fourth state of matter beyond solid, liquid, and gas. This plasma emits radiation across the entire electromagnetic spectrum, from long radio waves through infrared, through visible light, through ultraviolet, all the way up into X-rays. The peak of the emission, the wavelengths where the most energy is released, tends to fall in the ultraviolet and X-ray range, far beyond what human eyes can detect. If you were somewhere nearby, shielded miraculously from the radiation that would vaporize any material object, the accretion disk would not look like what science fiction films usually depict. Popular images of black holes often show a thin, gently glowing ring with a neat dark circle in the center. The reality would be both more chaotic and more strange. Gravitational lensing, the bending of light by the massive gravity of the black hole, would make the far side of the disk visible over the top and bottom of the black hole. You would see a ring of light that appears to wrap around the dark central shadow, with additional arcs and images forming as photons follow curved trajectories through the warped space-time. The disk would flicker and vary in brightness as turbulence rearranges the local density of gas. Magnetic fields threading through the plasma would create localized hotspots that rotate through your field of view. The whole system would shimmer and pulse with energy on timescales ranging from hours to years, and from a safe distance of millions of light years. All of this, the disk, the lensed light, the flickering, the radiation, would compress down to a single point, a point that, if it were placed 50 million light years away, would shine in our night sky with a brightness comparable to the full moon. Tone 618 is actually about 10.4 billion light years away, reducing its apparent brightness to something that requires large telescopes to detect. But its absolute luminosity, the actual power it is emitting, remains approximately 140 trillion times that of our Sun. Now let us talk about the jets. One of the most dramatic features of many active supermassive black holes is the production of relativistic jets, narrow beams of plasma and electromagnetic energy that shoot outward from the poles of the black hole at velocities approaching the speed of light. These jets are among the most powerful structures in the observable universe. A single relativistic jet from a large quasar can carry more energy than entire clusters of stars. They can extend for millions of light years in length, far beyond the boundaries of their host galaxy, punching through intergalactic space and depositing enormous amounts of energy in the surrounding medium. The mechanism driving these jets is one of the more elegant results in theoretical astrophysics. The spinning black hole and most large black holes are expected to spin because the matter they consume carries angular momentum, drags the fabric of space-time around with it. This effect, called frame dragging, was predicted by Einstein's equations and has since been confirmed observationally. Near a rapidly spinning black hole, space-time itself is in motion. Anything in the region just outside the event horizon, in a zone called the ergosphere, is dragged around with the black hole whether it wants to be or not. By extracting energy from this rotational dragging through mechanisms that involve magnetic fields threading through the disk and ergosphere, enormous amounts of power can be channeled into collimated outflows along the rotation axis. For Ton 618, the jets are real features of the system, though at its distance they are difficult to image in detail. What we know from modeling and direct observation is that they likely extend for significant distances beyond the host galaxy, and that the energy they deposit into the surrounding intergalactic medium has real effects on the large-scale environment. A quasar like Ton 6188 operating at its full luminosity does not just affect its immediate neighborhood. It heats and stirs the intergalactic medium across distances of millions of light years. It can suppress star formation in neighboring galaxies by preventing gas from cooling efficiently enough to collapse into stars. It participates in shaping the large-scale structure of the universe in ways that persist long after the quasar itself goes quiet. This brings us to one of the most counterintuitive insights of modern cosmology, one that completely reverses the intuition most people have about black holes. We tend to think of them as purely destructive, as cosmic vacuum cleaners that consume and annihilate, but supermassive black holes operating in this quasar mode are actually among the most important creative forces in cosmic history. The energy they pump into their surroundings regulates the growth of galaxies. Without that regulation, galaxies might grow too quickly, exhaust their gas reserves early, and stop forming stars long before the right chemical conditions for planets and life could develop. The feedback from supermassive black holes, the radiation, the jets, the winds from the accretion disk, all of it acts as a thermostat for galaxy formation, keeping the process slow enough and sustained enough for compact structure to emerge. There is a remarkable statistical relationship between the mass of a supermassive black hole and the properties of its host galaxy's central bulge, the dense stellar population surrounding the galactic core. This relationship, known among researchers by shorthand names referring to the velocity dispersion of bulge stars, holds across enormous ranges of galaxy size and black hole mass. It suggests that the black hole and its host galaxy grew together, co-regulating each other's development. They are not independent systems. They are partners in a feedback loop that spans billions of years. TON 618 at the extreme end of that distribution tells us what the partnership looks like under maximum conditions, what the galaxy scale equivalent of full throttle actually means. I want to pause here and mention something that came up in the comments section of videos on this topic because it reflects a genuine and thoughtful question that many people have. Someone asked, if light cannot escape from a black hole, how can we see any light from it at all? This question reveals an important subtlety. The light we detect from TON 618, the brilliant quasar glow, does not come from inside the event horizon. It comes from the accretion disk, which exists outside the event horizon. The disk is a structure of matter that has not yet fallen in. It is orbiting, slowly spiraling inward, and as it does, it releases energy. That energy takes the form of radiation, including visible light, that escapes outward. The black hole itself, the interior bounded by the event horizon, contributes no light. It appears as a dark shadow. But everything around it, the infolding material that has not yet crossed the boundary, radiates ferociously. A useful analogy is a drain in a bathtub. Water circling the drain has not yet gone down it. It is still in the tub, still visible, still making ripples. The drain itself is dark, but the water spiraling toward it is there, active, real. The event horizon is the drain. The accretion disk is the spiraling water. What we see is the water, not the drain. Now I want to take us into the physics of time near TON 618, because this is where the concepts become most strange and, I think, most beautiful. General relativity tells us that time is not a uniform background against which events take place. It is a dimension of space-time, woven together with the three dimensions of space, and its rate of passage is affected by two things, motion and gravity. An object moving very fast experiences time passing more slowly relative to a stationary observer. An object in a strong gravitational field experiences time passing more slowly relative to an object in a weaker gravitational field. These are not just abstract mathematical results, they are measured phenomena. The GPS satellites orbiting Earth need to account for both effects to maintain their precision, because they move fast enough and are high enough above Earth's gravitational well that their clocks run at a perceptibly different rate than clocks on the surface. Near TON 618, these effects are not subtle. They are overwhelming. Consider an observer hovering just outside the event horizon of TON 618. This is physically impossible in any practical sense, because the radiation environment near any active quasar would be instantly lethal, and because hovering against gravity that intense would require thrust that no plausible technology could provide. But, as a thought experiment, such an observer, if they survived, would experience time passing at a rate vastly slower than the rate experienced by someone far from the black hole. The relationship can be calculated using the Schwarzschild metric and related solutions to Einstein's field equations. Very close to the event horizon, the time dilation factor approaches infinity. An observer hovering just outside the horizon might experience a single second, while billions of years pass in the rest of the universe. From the outside, the situation looks different. An observer watching something fall toward the event horizon of TON 618 would see that object appear to slow down as it approached. The object's light would become increasingly redshifted, its color shifting toward the red and then the infrared and then the radio, its apparent brightness fading, its apparent motion slowing asymptotically toward zero. It would never appear to cross. It would approach and approach and approach, growing dimmer and redder, until it faded from detectability entirely. The crossing would never be observed from outside. From the perspective of the infalling object itself, no such pause exists. It falls through. The crossing is smooth. The event horizon, from the inside, is not a wall or a surface, but a moment in time, a point at which the future narrows to a single direction, and then, in whatever proper time the infalling object has available to it, it continues inward toward the singularity. What is the singularity? Here we reach the true frontier of physics, the place where our best current theories admit their own limitations. General relativity predicts that at the center of a black hole, a point of infinite density and infinite space-time curvature exists, the singularity. But physicists broadly agree that this prediction is a sign that general relativity is incomplete rather than a literal description of reality. Infinite density is not a physical condition. It is a mathematical indication that a theory has been pushed beyond its valid range of application. The laws of quantum mechanics, which describe the behavior of matter at the smallest scales, must become relevant when matter is compressed to extremely small volumes. General relativity does not incorporate quantum mechanics. Where the two sets of rules collide, neither gives fully trustworthy answers. The reconciliation of general relativity and quantum mechanics, the development of a theory of quantum gravity, is perhaps the deepest unsolved problem in fundamental physics. Several frameworks have been proposed: string theory, loop quantum gravity, causal set theory, and others. None is definitively established, but most physicists believe that whatever quantum gravity turns out to be, it will replace the prediction of infinite singularity with something finite, some structure of matter at the smallest possible scales that prevents the density from becoming truly infinite. The interior of TON 618, could we somehow access it, might be the most extreme natural laboratory for testing whichever of these frameworks is correct. One of the most deeply puzzling implications of this situation is the information paradox. Quantum mechanics, in all its standard formulations, conserves information. What this means, stated informally, is that if you know the exact quantum state of a system at one moment in time, you can in principle reconstruct its exact state at any other moment, past or future. Information is never destroyed. It may become scrambled, dispersed, hidden, but it is never annihilated. This is a fundamental feature of quantum mechanics, and it is held up through every experiment and observation we have made. Now consider what happens when matter falls into a black hole. The matter carries information, the quantum states of every particle that composes it. It crosses the event horizon. From outside, that matter is gone forever. Nothing can come back. Classically, the information is destroyed, but quantum mechanics says information cannot be destroyed. Contradiction. Stephen Hawking deepened this problem in the 1970s when he calculated that black holes are not perfectly black. Due to quantum effects at the event horizon, pairs of virtual particles can be created in a process where one particle falls into the black hole and one escapes as real radiation. This Hawking radiation carries energy away from the black hole, and in principle, over an enormous timescale, it can cause the black hole to slowly evaporate. For a black hole as massive as TON 618, this process is so slow that it would take a time many orders of magnitude longer than the current age of the universe to have any significant effect. But in principle, it implies that every black hole eventually evaporates, releasing its mass as radiation. The question is whether that final radiation carries the information about everything that ever fell in, or whether the information is lost. Hawking originally argued it was lost, which would violate quantum mechanics. Later work, including the development of insights from string theory and the study of something called the ADA/CFT correspondence, has shifted the consensus toward a belief that information must be preserved, that it somehow escapes encoded in the subtle correlations of Hawking radiation. But the mechanism by which this happens remains deeply unclear. Some recent proposals involve what are called firewalls, dramatic departures from general relativity's predictions at the event horizon. Others involve modifications to the concept of the interior itself. The debate remains live, unresolved, and centrally important, and in the background of all of it sits TON 618, the most massive black hole we have ever measured, patient and distant, carrying the ultimate stakes version of the problem. Now I want to take a step back from the physics and say something about scale that I think gets lost in the numbers. Every civilization that has ever looked up at the night sky has had to confront the fact that the sky is larger than it is. The stars are not painted on a dome above us. They are real objects at real distances, and those distances are staggering even by stellar standards, let alone by the standards of a human life. But for most of human history, the universe that people imagined was orders of magnitude smaller than the universe we have measured. The ancient Greeks, brilliant and precise in their reasoning, believed the stars were embedded in a sphere that was, in the most expansive ancient estimates, a few million kilometers away. This was wrong by a factor of many billions. Medieval astronomers placed the stars farther, but still incomprehensibly closer than the truth. Even in the early 20th century, there were serious astronomers who believed the Milky Way was the entire universe, and that the fuzzy smears visible through large telescopes in other directions were merely clouds of gas within our galaxy. Then Edwin Hubble measured the distance to Andromeda in the 1920s, confirmed that it was far beyond any plausible bound of the Milky Way, and in doing so, expanded the known universe by an almost unimaginable factor. And the universe has continued to expand, not in the physical sense alone, but in the sense of what we know exists within it. Each time we have built a better telescope, pointed it somewhere carefully, and asked how far is that, the answer has come back larger than before, larger and more filled with structure than before. TON 618 was first noticed as a peculiar radio source in the 1970s. Its true nature, a quasar of extraordinary luminosity, was established through subsequent observations. Its mass, 66 billion solar masses, was measured using a technique called reverberation mapping, which exploits the delayed response of gas clouds surrounding the central engine to changes in the quasar's brightness. The mass measurement has been refined multiple times as better data became available, and it remains among the highest confidently measured masses for any single gravitational object in the observable universe. There may be more massive black holes. There almost certainly are in galaxies too distant to observe, or in orientations that hide their quasar emission from us. The observable universe contains an estimated 2 trillion galaxies. Each of them, or nearly each, harbors a supermassive black hole. Most of those black holes are dormant, not currently accreting at the rates that make them glow as quasars, but they are there in the cores of their galaxies, shaping the motion of billions of stars through gravity alone. The dormant black hole at the center of the Milky Way, called Sagittarius A, has a mass of about 4 million solar masses. It is, relative to TON 618, a minnow. It has enough mass to be the gravitational anchor of our entire galaxy, enough to make stars in the galactic center orbited at thousands of kilometers per second, but it is 16,000 times less massive than TON 600 and 618. The difference in scale between those two numbers is roughly the same as the difference between a grain of sand and a large building, and yet both follow the same equations. The same mathematics that describes the 4 million solar mass black hole in our own galaxy describes the 66 billion solar mass object 10 billion light-years away. The universe uses one set of rules. It writes them in different sizes, but the grammar does not change. That universality is one of the most quietly astonishing facts in all of science. The equations on a chalkboard in a laboratory on Earth describe what happens at the center of a galaxy billions of light-years away. They describe what happened before Earth existed. They describe processes occurring in environments so extreme that no material made of matter could exist within them, and they do so with precision that has never been falsified in any test we have been able to perform. There is something deeply moving about that if you let it land. We are small creatures, on a small planet in an ordinary galaxy, in an unremarkable corner of a universe that stretches for tens of billions of light-years in every direction. We live for, at most, a century. Our senses perceive an almost invisibly thin slice of the electromagnetic spectrum. We can only directly observe a tiny fraction of the matter and energy that the universe actually contains. We are, by any reasonable cosmic accounting, profoundly limited. And yet, we can calculate the mass of an object 10.4 billion light-years away by measuring the time delay between brightness fluctuations in its core and the response of gas clouds at known distances from it. We can determine how fast the universe was expanding 10 billion years ago by measuring the shift in wavelength of specific atomic emission lines in the spectrum of TON 618's accretion disk. We can infer the temperature of plasma orbiting its event horizon, the orientation of its magnetic fields, the probable spin of the black hole itself, all from patterns in light that has been traveling since before Earth existed. This is what human curiosity extended to mathematics and instrumentation can accomplish. It is one of the most remarkable things our species does. and it costs almost nothing to participate in it. You do not need a telescope. You do not need a degree in physics. You need only the willingness to sit with the ideas long enough for them to open up, which is exactly what you are doing right now. Let me take you now into some of the latest thinking in black hole physics. Things that have developed or sharpened significantly in just the past few years. The Event Horizon Telescope collaboration, which produced the first direct images of a black hole, released its image of Sagittarius A in 2022, following the landmark image of the black hole at the center of the galaxy M87 in 2019. These images do not show the black hole itself, which by definition cannot emit detectable light. They show the shadow cast by the black hole against the luminous background of the surrounding accretion structure. The bright ring surrounding the dark central shadow is formed by photons following circular orbits around the black hole before escaping outward. It is called the photon ring. Its shape, size, and brightness contain information about the mass, spin, and space-time geometry of the black hole. TON 618 is far too distant and far too small on the sky to be imaged this way with current technology. Its angular size, as seen from Earth, is tiny even compared to M87's black hole, but the theoretical and analytical methods developed through the Event Horizon Telescope program have deepened understanding of accretion physics in ways that improve our ability to interpret the data we do have from distant quasars. Meanwhile, the emergence of gravitational wave astronomy, following the first detection of gravitational waves by LIGO in 2015, has opened a completely new observational window on the universe. Gravitational waves are ripples in spacetime itself, produced whenever massive objects accelerate asymmetrically. The mergers of stellar mass black holes, now detected with impressive frequency, have provided new tests of general relativity in the strong field regime. Looking forward, space-based gravitational wave detectors like LISA, the Laser Interferometer Space Antenna, planned for launch in the 2030s, will be sensitive to the much lower frequencies produced by the inspiral and merger of supermassive black holes. These events, when two supermassive black holes spiral together in the aftermath of a galaxy merger, are among the most energetic phenomena in the universe since the Big Bang. Detecting them would provide direct measurements of black hole masses and spins that are currently only accessible through indirect means. It is possible that some of the gravitational wave events that LISA will detect will be related to objects like TON 618 or to the class of ultramassive black holes that TON 618 represents. It is also possible that future observations with next-generation radio telescopes will resolve enough detail in the quasar jets of distant objects to yield information about the spacetime geometry close to the event horizon. The observational landscape is expanding. The questions that TON 618 raises are not merely philosophical. They are questions that are actively being pursued, that will be sharpened and constrained by data that does not yet exist. If you have been wondering where you fit into all of this, as a listener, as a human being lying in the dark thinking about something 10 billion light years away, I want to spend some time on that now, because I think it is the most important part. There is a view of science, sometimes encouraged by how it is taught and how it is popularized, that sees it as a collection of facts to be learned and stored, a growing encyclopedia of what we know, with each entry settled and complete. This view is not wrong exactly, but it is incomplete in a way that strips out the living quality of the enterprise. Science is not primarily a collection of facts. It is a relationship with uncertainty. It is the practice of asking, what do we actually know, and how do we know it, and what would change our minds? And in that practice, the boundary between what is known and what is not a wall at the edge of a map. It is a living frontier, constantly advancing in some directions and revealing new depths of mystery in others. TON 618 sits right at that frontier. Its existence is established, its mass is measured, its distance is known, but the mechanism of its formation is not fully understood. The physics of its interior cannot be directly accessed. The resolution of the information paradox it embodies has not been reached. The question of what happens at the singularity it contains is unanswered, and these are not peripheral questions. They go to the heart of what matter is, what time is, what information is, and how the universe handles its own most extreme expressions. Every astronomer who studies quasars, every physicist who works on black hole thermodynamics, every theorist who writes equations about quantum gravity is in some sense conducting a conversation with objects like TON 618, asking it what it knows, straining to hear the answer across billions of light years and billions of years of time. The light it sends us is patient. It carries the same information whether we are ready to read it or not. And our ability to read it is slowly improving with each generation of instruments and each generation of theorists and each generation of people who decided that the universe was worth understanding. You are part of that lineage, not because you are a professional scientist, though perhaps you are, but because you are here, paying attention, allowing the questions to open up inside you. The act of genuine curiosity directed outward toward the cosmos is not separate from the scientific enterprise. It is its foundation. Every measurement ever made began with someone asking, "What is that?" and caring enough about the answer to find out. In the earliest days of radio astronomy, the bright point catalogued as TON 618 was just a number in a survey. Someone looked at it and noticed it was unusual. Someone else followed up. Someone else measured its spectrum and noticed the redshift. Someone else realized what the redshift implied about its distance and therefore its luminosity. Someone else modeled the accretion physics well enough to estimate the black hole's mass. Each step was the work of people who were curious enough and careful enough and persistent enough to keep asking the next question. The 66 billion solar masses we associate with TON 618 today is the accumulated result of decades of that kind of work by people who probably had no idea when they started where the question would lead. This is also worth saying. You do not have to be anxious about the scale of what we have been discussing. I know that for some people, the contemplation of cosmic distances and timescales produces not wonder, but a kind of vertigo, a feeling of irrelevance or smallness that tips toward anxiety rather than awe. If that is where you are, I want to say directly, your smallness relative to the cosmos does not diminish your significance within it. Scale is not the same as importance. The universe is almost entirely empty space, and the fraction of it that is matter, and the fraction of that matter that is capable of being curious, and the fraction of curious matter that is actually exercising that curiosity right now is vanishingly small, which means that curiosity is not the default state of the universe. It is the exception. You are the exception. The atoms that make up your body have existed for billions of years without once, in all their previous arrangements, being able to think about TON 618. Tonight, they can. That is not nothing. In fact, I would argue it is everything. The universe is vastly old and vastly large. It has been running its processes largely without anyone watching for most of its history. Stars have burned and collapsed in galaxies that are now too far away for their light to ever reach us. Black holes have formed and grown in corners of the cosmos that will remain permanently beyond our observational horizon. Whatever happened there, whatever extreme events, whatever extraordinary physics played out in those inaccessible regions, occurred without witnesses. They occurred without understanding. The universe does not require understanding to function. It runs the equations whether or not anyone is watching. But understanding happened anyway, in this one small corner of this one ordinary galaxy. On this one pale blue dot, evolution produced creatures capable of looking outward and asking why, capable of building instruments that extend sight beyond what eyes can see, capable of writing mathematics that describe space-time near black holes before ever directly observing one, capable of measuring the mass of an object billions of light years away by timing the delay between brightness variations. That capacity is extraordinary. It did not have to exist. There is no physical law that requires a universe to produce curious observers. And yet, here you are. And here I am. And here is TON 618. Patient as light, still sending its ancient signal outward through the expanding dark, reaching the small instruments of a species that has only just begun to listen. I want to close this section of our journey with something that I think deserves to be said slowly and clearly, because it tends to get lost in the rush toward impressive numbers. The light from TON 618 that reaches our telescopes left its source before the sun formed, before Earth formed, before the ocean formed, before the first bacterium divided in a warm tide pool somewhere on a cooling rocky surface. It left before life existed on this planet, before any mind, any awareness, any capacity for experience existed in this corner of the galaxy. That light traveled for over 10 billion years. It passed through expanding intergalactic space. It was stretched in wavelength by the growth of the universe. It was bent by the gravity of everything it passed near. It interacted with the diffuse hydrogen that fills the space between galaxies, leaving subtle imprints in its spectrum that tell us about the state of the early universe. And then it arrived, and someone with a carefully calibrated instrument and an understanding of spectroscopy looked at the resulting data and understood what they were seeing. That chain, from the accretion disk of a black hole, 66 billion times more massive than the Sun, across 10 billion light-years and 10 billion years of time, to the consciousness of a being who can recognize it for what it is one of the longest causal chains in the history of the cosmos. And you are at the end of it, right now, tonight. The photons have already arrived, the measurements have already been made, the knowledge exists, and you are engaging with it, turning it over, feeling its weight, letting it change something about how you understand your place in the universe. That is not a small thing. I want you to know that. Now let us go a little deeper into the strangeness of what black holes do to time and space, because some of the most counterintuitive results of general relativity become most vivid when you apply them at the scale of TON 618. We established earlier that time passes more slowly near a strong gravitational field, but the way this is usually presented, as a single number or ratio, does not quite convey the lived geometry of it. Let me try to approach it differently. Imagine two clocks. Clock A is placed in deep space, far from any significant mass, experiencing what physicists call flat space-time. Clock B is placed just outside the event horizon of TON 618. Both clocks are carefully synchronized at the beginning. Clock A ticks at 1 second per second, by its own reckoning and by the reckoning of the distant universe it is embedded in. Clock B also ticks at 1 second per second by its own reckoning. From Clock B's perspective, nothing unusual is happening. Time feels the same, but as measured by Clock A, Clock B is running extraordinarily slowly. Each second that passes for Clock B corresponds to a much larger number of seconds for Clock A, the exact ratio depending on how close Clock B is to the horizon. As Clock B approaches the horizon, this ratio approaches infinity. Seconds for Clock B become years, centuries, eons for the rest of the universe. The horizon itself is the boundary where this dilation becomes complete. At the horizon, from the outside, time freezes entirely. This is not merely a consequence of signal delay or the time it takes light to travel from one clock to the other. It is a real feature of space-time geometry. The rate of time passage is literally different at different locations in a gravitational field. The clocks disagree not because of measurement error or propagation delay, but because time itself runs at different rates at different gravitational potentials. For everyday purposes near Earth, this effect is tiny but real. The difference in gravitational potential between sea level and the altitude of the GPS satellite constellation is small enough that it only amounts to a few microseconds per day, but those microseconds matter. Without correction, GPS systems would accumulate errors of several kilometers per day. The correction is made using the formulas of general relativity, and it works. This is one of many examples of a purely theoretical prediction of general relativity, formulated a century ago from mathematical reasoning alone, being confirmed with enough precision that we rely on it daily in technology that billions of people use. Near TON 618, the same physics operates, but at a scale that makes the GPS correction look infinitesimal. The gravitational potential gradient near the event horizon of a 66 billion solar mass black hole would produce time dilation factors that are not small corrections but enormous ratios. An observer hovering close to the horizon, experiencing what they would call a single day, might return to find that millions or billions of years had passed in the rest of the universe. This is the physical basis for speculative ideas in science fiction about time travel near massive objects, and while those fictional scenarios are typically exaggerated and oversimplified, the underlying physics is real. Gravity dilates time. The stronger the gravity, the greater the dilation. TON 618's gravity is the strongest we have measured anywhere. There's also the phenomenon of gravitational redshift, when light escapes from a strong gravitational field. it loses energy. Light is a wave, and its energy is determined by its frequency, the number of wave cycles per second. When light loses energy, its frequency decreases, which means its wavelength increases, shifting it toward the red end of the spectrum. This is why light from the surface of a star is slightly redshifted relative to light from the same atoms in a laboratory. The star's gravitational field is strong enough to extract a measurable amount of energy from escaping photons. Near the event horizon of TON 618, the gravitational redshift is not slight. Photons escaping from just above the event horizon are extremely redshifted relative to photons emitted at larger distances. They carry far less energy when they escape than they had when they were emitted. And this redshift is observable from Earth as a component of the total redshift we measure from TON 618. On top of the much larger cosmological redshift produced by the expansion of the universe over 10 billion years of travel, the superposition of these effects, gravitational redshift close to the source and cosmological redshift over the journey, means that a photon emitted from the innermost visible region of TON 618's accretion disk as hard X radiation might arrive at Earth as a faint radio wave or microwave. The same physical event, the same quantum transition that released the photon, produces a signal that we detect at a completely different wavelength than it was emitted at, and yet we can reconstruct the original conditions from the patterns we observe, because we understand both the gravitational redshift and the cosmological expansion. The physics is consistent, the universe is legible, even when it is operating at these extremes. Let me now address something that the comment section of videos on this topic reveals is a genuine source of wonder and confusion for many people. The question of what it would mean to fall into TON 618, not practically, because practically this is not possible for anything made of matter that originated in our solar system at any point in the foreseeable future. But conceptually, what does the physics actually say about that experience? We have already touched on some aspects of this, but let me build a more complete picture. Far from TON 618, you are in familiar territory. Space is essentially flat. Time passes at its ordinary rate. The laws of physics behave as they do everywhere else in the universe. TON 618 would appear to you as a bright point of light, brilliant enough to be visible at great distances. Its accretion disk too small in angular size to resolve with the naked eye, but clearly the source of extraordinary energy. As you approach, the effects of gravitational lensing begin to become visible. Light from the accretion disk on the far side of the black hole bends around it, making the disk appear to wrap around the dark central shadow. You begin to see multiple images of the disk, produced by photons that have traveled around the black hole before reaching you. The visual environment starts to feel strange, not because anything is physically wrong, but because space-time is curved enough to produce optical effects that your visual system was not evolved to interpret. Closer still, you enter the region where the tidal forces, the difference in gravity across your body, become significant. For TON 618, this transition happens relatively close to the horizon because the horizon is so large. But it does happen eventually as you approach. The force pulling on the side of you facing the black hole is stronger than the force pulling on the side facing away. This differential stretches you in the radial direction and compresses you laterally. This is the beginning of the process usually called spaghettification. Though for TON 618, the onset is gentler and occurs closer to the horizon than it would for a smaller black hole. The radiation environment intensifies dramatically. The accretion disk, which we have been ignoring for purposes of this thought experiment, would in reality have destroyed you long before any of these gravitational effects became significant. The X-ray and gamma-ray flux, near an active quasar like TON 618, would vaporize any known material in fractions of a second at close range. But we are imagining you as an observer, not a material object, so we continue. At the event horizon, you cross. From your perspective, the crossing is smooth. There is no flash, no sudden change in how you feel. General relativity, within its domain of validity, predicts that the crossing is locally unremarkable. The physics continues to work. Your clock continues to tick. You continue to think, perceive, experience. What has changed is purely geometric. The future light cone, the set of all possible futures accessible to you, given the constraint that nothing can exceed the speed of light, now points entirely inward. Every direction that you might travel, no matter what direction you choose, brings you closer to the center. There is no path that leads outward. The horizon is not a wall in space. It is a moment in time, and once past it, every possible moment ahead of you lies inward. Inside, space-time continues. The geometry is different from outside, but it is described by equations, by mathematics, by structure. General relativity does not simply go silent inside the horizon. It continues to make predictions, and those predictions describe a space-time that is dynamic, evolving, directing all future pointing paths inward. The singularity, in the classical general relativistic description, is not a place in space, but a moment in the future of every inward-falling observer. It is not something you approach in the spatial sense. It is something that is coming in the temporal sense, regardless of your spatial position inside the horizon. At some proper time after crossing, however long the geometry allows, you encounter conditions so extreme that general relativity's equations lose validity. The density, the curvature, the energy scales all exceed the regime where we can trust the theory. What happens then is genuinely unknown. It is the edge of our current physics, and in that unknown many of the deepest open questions of theoretical physics are embedded. What does it mean that we cannot know? It means, most fundamentally, that the universe contains regions from which no information can ever reach us. We are not just saying we do not have good enough instruments. We are saying that the laws of physics, which require nothing to outrun light, which build causality into the structure of space-time itself, prevent the information from ever reaching us regardless of what technology we develop. There are truths about the universe that are, in a precise physical sense, inaccessible to any observer positioned outside the horizon. That is a genuinely new kind of epistemic limitation, not the ordinary limitation of insufficient data or insufficient understanding, but a structural limitation built into the fabric of space-time. This is the event horizon as an epistemological boundary, the boundary not just of travel, but of knowledge, and the recognition that such boundaries exist, that there are things we cannot know, not because we are not smart enough, but because the universe's geometry prevents it, is one of the more philosophically significant insights to emerge from the physics of the 20th century. I find that recognition strangely comforting, not because I enjoy ignorance, but because it means the universe is larger than our instruments. It means that even our best theories, our most carefully tested understanding of how reality works, points toward regions where it admits its own limitations. Science is not pretending that it has everything figured out. The very best science, the most precise and careful and deeply tested science, points clearly at its own horizon and says, we cannot see past there. Not yet, perhaps not ever. That honesty is, I think, one of the most admirable things about the scientific approach to knowledge, and it is modeled in the most literal physical sense by the event horizon of TON 618. We are now moving toward the end of our journey tonight, and I want to spend some time on what the future of this subject looks like, because we are living through a period of genuine transformation in our ability to observe the universe, and some of the most exciting results in black hole astrophysics are yet to come. The James Webb Space Telescope, operational since late 2021, is already finding supermassive black holes at earlier cosmic times than previously known, in galaxies that formed within 1 billion years of the Big Bang. These discoveries are refining and in some cases challenging our models of early galaxy formation. The black holes Webb is finding are not as massive as TON 618, but they are massive and they are early, and their existence is pushing theorists to revise their estimates of how quickly massive black holes can form. The picture that is emerging is one in which the early universe was far more efficient at building extreme structures than our simplest models predicted. The Vera C. Rubin Observatory in Chile, now beginning operations, will conduct the most comprehensive time-domain survey of the southern sky ever attempted, imaging billions of objects repeatedly over the course of a decade. Among the phenomena it will catalogue are tens of thousands of quasars, many newly identified, with light curves, measurements of how their brightness varies over time. That will reveal details about their accretion physics and the properties of their central black holes. The statistical dataset this will provide of quasar behavior across cosmic time will be unprecedented. Radio telescope arrays, including the next generation, Very Large Array, and the Square Kilometre Array, are being developed with capabilities that will allow much higher resolution imaging of quasar jets and accretion structures at greater distances than before. The prospect of imaging the jet base of a distant quasar, the region very close to the event horizon where the jet is launched, has been a long-standing goal of radio astronomy, and these facilities may bring it within reach for some nearby targets. And then there is the gravitational wave frontier. LISA, if it launches as planned, will be sensitive to the gravitational waves produced by supermassive black hole mergers at cosmological distances. These mergers are expected to occur throughout the universe's history, and the gravitational wave signatures will contain direct information about the masses, spins, and orbital parameters of the merging black holes. The prospect of detecting a gravitational wave signal from a merger involving an ultramassive black hole of TON 618's class, a merger that might have occurred billions of years ago and whose gravitational waves are only now arriving at our position, is not merely speculative. It is a concrete scientific goal, with mission design parameters being worked out in detail. Meanwhile, theorists are making progress on the foundational questions: the holographic principle, the idea that all the information contained in a volume of space can be encoded on its boundary surface, emerged from the study of black hole thermodynamics and has become one of the central ideas in attempts to unify quantum mechanics and gravity, the anti de Sitter conformal field theory correspondence. A mathematical equivalence between a gravitational theory in one space and a quantum theory on its boundary has provided new tools for computing properties of strongly coupled quantum systems. These developments, emerging from the study of black holes, are connecting to physics in unexpected ways, informing condensed matter physics, quantum information theory, and the foundations of quantum mechanics itself. The black hole is not just an astrophysical object. It is a nexus where the deepest questions of fundamental physics intersect. Every advance in our understanding of black holes is simultaneously an advance in our understanding of gravity, of quantum mechanics, of information, and of space-time itself. TON 618, at the extreme end of the spectrum, is the most massive version of that nexus. It is the universe's most extreme laboratory, running an experiment that began before Earth formed, whose results are still coming in, and which we are only beginning to know how to read. Here is something I want you to carry with you as this night ends or deepens, whichever direction you are heading. The fact that TON 618 exists, 66 billion solar masses of collapsed matter anchoring a galaxy 10 billion light-years away, does not make you smaller. It makes the universe larger, and a larger universe is a richer one. A universe that can produce both TON 618 and you, that can operate simultaneously at scales of billions of light-years and at the scale of a thought that runs the same physical laws from the Planck scale to the cosmological horizon. That is not a universe that renders you irrelevant. It is a universe of extraordinary depth and range, and you are part of its range. The atoms in your body are not merely stardust in a poetic sense. They are genuinely material that has existed through multiple stellar lifetimes, that was present in conditions not entirely unlike those in the accretion disks of early quasars, that has been organized and reorganized by the same physical forces that govern TON 618, and that arrived at this particular configuration, this arrangement that can wander about its own origins and the origins of the universe by a path of extraordinary improbability. You are not just looking at the universe from outside it. You are a specific local expression of it, a temporary configuration of 10 billion-year-old matter that has arrived at the capacity to ask, what are we, and where did we come from? That question, and the journey we have taken tonight to approach it through one particular astonishing object, is not separate from the universe. It is the universe, doing something remarkable. The same gravity that pulled gas into the accretion disk of TON 618 eventually organized itself into planetary systems, into chemistry, into life, into minds capable of measuring the very object that contributed to creating the conditions that made minds possible. That is not a poetic stretch. It is, to the best of our current understanding, a literal description of causal history. The light from TON 618 is still traveling. Photons that left its accretion disk a billion years after the ones currently in our telescopes are now somewhere in the vastness of intergalactic space, a billion light-years closer to Earth than they were when they started. 9 billion light years still to go. They will arrive here if Earth still has instruments capable of receiving them in 9 billion years. By then, our sun will have already become a red giant and likely swallowed the Earth. Whatever receives those photons, if anything does, will not be us. But the photons will come, and the photons currently arriving, the ones being collected right now by telescopes, the ones being converted into data that researchers are analyzing as you listen to this, those photons carry a message from the early universe, a message about what the universe could build, about what gravity can do with enough mass and enough time, about the extreme endpoints of physical law. The message has been traveling for 10 billion years. It has arrived, and we are learning to read it. That is where we are in the story. Not at the end. Not even close to the end. We are in the early chapters of understanding what the universe actually is. We have measured the mass of Ton 618. We have confirmed the existence of gravitational waves. We have imaged the shadow of a black hole event horizon. These are extraordinary achievements, and they are also the very beginning. Future generations will look back on this moment the way we look back on Galileo pointing his telescope at Jupiter and discovering that it had moons, as the first faltering steps toward understanding something much larger than was visible at the time. I want to end by going back to where we began, to you, right now. In your specific place in the world, at this specific moment in time, you have spent these hours traveling in thought to one of the most extreme objects in the observable universe. You have thought about mass measured in billions of suns and distances measured in billions of light years and time measured in billions of years. You have sat with the counterintuitive results of general relativity, with the strangeness of the event horizon, with the open questions at the boundary of our understanding, and through all of that you brought something that Ton 618 does not have. You brought the capacity to be here, present, aware, curious, the capacity to be moved by something this large and this distant. The universe is not impressed by itself. It does not know it is vast. It does not experience its own elegance. The equations run, the photons travel, the black holes consume and radiate, and none of it is accompanied by any sense of wonder, because wonder requires a subject. It requires something that can notice and feel surprised and ask why. The universe produced that capacity here, in us. And we are using it right now, in this quiet moment, to reach towards something 10 billion light years away and say, we see you, we are trying to understand you. We are grateful that you are part of the same universe as us. Ton 618 will not receive that message. Nothing we send can cross 10 billion light years in any meaningful time frame. But the message matters anyway, not because it will be received, but because sending it is part of what it means to be the particular kind of creature that we are. Curious, reaching, unwilling to accept that the universe is simply too large to think about. It is not too large to think about. We have been thinking about it tonight, and the thinking is its own reward. The understanding, partial and imperfect, and constantly being revised, is its own form of beauty. The questions that remain open are not failures. They are invitations, and the light from Ton 618, patient and ancient and still arriving, will be there tomorrow, carrying more to learn, waiting for the instruments and the minds that will be able to ask better questions than we can ask today. For now, let your thoughts settle. Let the scale of what we have touched tonight breathe around you without demanding anything. The universe has been running for 13.8 billion years. It will continue to run for timescales so long that 13.8 billion years will seem, in retrospect, like the very beginning of a very early morning. There is no hurry. There is no deadline. There is only the quiet, extraordinary fact of being here, being aware, being the place in the universe where the universe notices itself. Wherever you are, I hope you sleep well. I hope the scale of what we discussed tonight gives your thoughts room to breathe rather than reasons to worry. The problems of your life are real and they matter and they will still be there tomorrow, but they exist inside a universe that contains Ton 618. Which is to say, they exist inside a universe that is unimaginably large, unimaginably old, and unimaginably rich with structure and process and law. And somehow, in all of that, your particular arrangement of atoms found its way here, to this night, to this curiosity, to this moment of contact with something larger than anything ordinary language was built to hold. That is not a small thing to be, that is an astonishing thing to be. If this journey opened something for you, if it gave your mind a place to rest that felt larger than the usual rooms, consider coming back. Consider sharing it with someone else who might need a bigger sky to think under. The quiet act of pointing someone towards something vast and strange and beautiful is one of the better things we can do for each other. Rest now. The universe will still be there in the morning, all 100 trillion stars of it, all 66 billion solar masses of ton 618 anchoring its ancient galaxy at the edge of the observable cosmos. All the photons still crossing the dark, still carrying their 10 billion-year-old messages, still faithful to the physics that sent them, still arriving, still teaching, still giving us something extraordinary to wonder at. Sleep well.